In a previous lecture, we did a calculation to show that when liquid water boils, that change is associated with an enthalpy change of 44 kilojoules for every mole of water that undergoes the change. And we should recognize that this particular change here, liquid water going to gaseous water, that just represents a change of state. It's boiling or it's evaporating. And so this change here, actually, we would call this the enthalpy of vaporization of water. And all substances that undergo vaporization have an associated enthalpy of vaporization. And this is similar for all different types of phase changes. We should recognize that there's an enthalpy of vaporization for liquid nitrogen. There's an enthalpy of vaporization for liquid oxygen. There's an enthalpy of vaporization for liquid zinc. And these enthalpy changes for various phase changes have been figured out and tabulated. And you can look them up. You can look up the enthalpy of vaporization of water, the enthalpy of vaporization of zinc, all the different elements. And you can look this up for all of the different phase changes as well. So we're gonna remind ourselves what all the different phase changes are and look at some of the symbolism that's used to describe all these different phase changes. So in this case, what would be written is delta H with a subscript vape for vaporization. And if you see this, you know that what's being referred to is the enthalpy change to get something to go, whatever that something is, from a liquid to a gas, the enthalpy of vaporization. And the enthalpy of vaporization is always positive. Let's think about whether that makes sense. The enthalpy of vaporization is always positive. Well, if you think about it, if you want to make something evaporate, that something has to go from a liquid to a gas. In order to go from a liquid to a gas, it should make sense that you're going to have to increase the kinetic energy of the particles. And if you're going to increase the kinetic energy of particles, you got to put energy into the system. So it should make sense that enthalpies of vaporization are always positive. Now what if I write this in the reverse direction? So instead of liquid water going to gaseous water, I have gaseous water going to liquid water. In this case, the enthalpy change would just be the opposite, because if you flip the equation, you change the sign, and we'd no longer call this the enthalpy of vaporization, but rather the enthalpy of condensation. And it's always going to be the case for a particular substance that the enthalpy of vaporization is going to be the opposite of the enthalpy of condensation. We can go through this for the other phase changes. For example, we can think about, let's think about this. Liquid zinc going to solid zinc. We can call this the enthalpy of fusion, is what they call it. It's the enthalpy of freezing. I mean, this represents freezing, a liquid going to a solid. And let's see if I have this here. Yes, the enthalpy of fusion of zinc is going to be a negative 102 kilojoules for every mole of zinc that undergoes, oh, I'm sorry, that's per gram. This is going to be kilojoules per gram. So it's going to be 102 kilojoules. That's joules, not kilojoules. Sorry. No, that's negative. It's 102 joules for every gram of zinc that freezes. And this may sound a little weird that freezing is exothermic, is what we're saying here, right? Delta H is negative. So freezing gives off energy. And I remember the first time I heard this, it didn't make sense to me that freezing would be exothermic. But if we think about it this way, this is often how I think about phase changes. I just sort of draw a diagram like this, where I have increasing, I think about it as energy on the y-axis, and then I sort of have time. This is just what's happening over time during a particular process. And in the process of freezing, what's going on is you have a liquid going to a solid. And what I try to think about when I'm doing this is I try to think about what is going on with the kinetic energy of the particles as I go from a liquid to a solid. Well, in a liquid, particles are pretty well free to move compared to a solid, right? In a solid, those particles are locked in place. And if particles are locked in place, the kinetic energy of those particles are going to be relatively low. So on the solid side, I'm going to draw my particles relatively low here. And on the liquid side, I'm going to draw the particles a little relatively higher in terms of kinetic energy of the particles because they're freer to move. Motion, kinetic energy, those go together. So I'm going to put that a little higher here on the diagram. And I'm going to write a liquid here and a solid here. And now it helps me visualize why freezing is an exothermic process. Pretty easy to see that in order to go from a liquid to a solid, I've got a drop in energy. And to drop in energy, that energy's got to go somewhere if I'm losing it. So that energy will be released to the surroundings. And if the system is losing energy, that's an exothermic change. So my delta H of fusion is going to be a negative 102 joules per gram. If we were to flip this around and look at zinc solid going to zinc liquid, the delta H for this is going to be a positive 102 joules for every gram. We just flip the sign. And in this case, we'd be going the reverse direction on that diagram from the solid, low kinetic energy of particles, to a liquid, higher kinetic energy of particles. Solid to a liquid is the fusion. Sorry, this is the enthalpy of fusion. And this would be the opposite of that. So I apologize for that. The enthalpy of fusion is defined as the enthalpy change required to take something as a solid and convert it to a liquid. In practice, we remember that if I have the enthalpy change for something that is undergoing melting, that's going to be the opposite of the enthalpy change for that same thing undergoing freezing. There's another set of phase changes we have to cover here. You remember what they are? Sublimation and deposition. Let's run through those. We know carbon dioxide. Well, let's start with a solid. We know carbon dioxide sublimes. So the enthalpy change required to get a gram or a mole, whatever it happens to be, of carbon dioxide going from a solid directly to a gas without passing through the liquid state, we'd call that the enthalpy of sublimation. And if we flip this, CO2 gas going directly to the solid state, again without passing through the liquid state, we'd call this the enthalpy of deposition. And just like all the other ones, we see that because I went from here to here, all I did is reverse the equation. We're going to recognize that whatever the enthalpy of sublimation is for a particular substance, is going to be the opposite of the enthalpy of deposition for that particular substance. Just change the sign.